A very good morning everyone. I am Ekansh Agrawal and today I will be taking a lecture on soil mechanics purely from GATE perspective. I will be starting from very basic, considering it a fresh new subject for all of you, and we will even solve the GATE previous year questions at the end of the session. Before starting, I will just brief you the syllabus for geotechnical engineering. Regarding GATE, the syllabus is defined under this main heading geotechnical engineering. And we have two subheadings under this. One is soil mechanics, other is foundation engineering. Foundation engineering consists with all shallow foundation, deep foundation, pile foundation, etc. We will be dealing with these foundations later on. Today we will start with soil mechanics. Soil mechanics subtopics are origin of soil. What we want to cover it today: origin of soil, and then we're going to have three-phase system and phase interrelationship. Before this thing, I will just give you a brief of three technical terms regarding soil engineering. One is soil mechanics, second is soil engineering, and third is geotechnical engineering. As such, these questions won't be asked directly in GATE, but we should know these questions, know these terms, even actually from the interview point of view. First is soil mechanics. We have a word mechanics over here. Mechanics means deals with action of forces. Anything related to mechanics is basically something dealing with action of forces. So soil mechanics becomes deals with action of forces on soil. Actually, this term was coined by Carl Terzaghi. He is called father of soil mechanics in 1925. Just for the information I'm telling you, it's not that important from GATE point of view. Then when we talk about soil engineering is actually application of soil mechanics. Application of soil mechanics. All the application which we are using in engineering, from foundation, investigation, design, construction, foundation, retaining wall, etc. all this comes under soil engineering. We are applying soil mechanics to engineering actually. And when we talk about geotechnical engineering, it is actually a much broader term. It includes soil engineering, it includes rock mechanics, it also includes geology. So as not an issue, geotechnical engineering and soil engineering are synonymously used, so not a big deal, but we should actually know the basic difference if someone asks us in the interview. Now coming to our syllabus part, we are starting with origin of soil. Origin of soil. Question arises, what is soil? We need not to complicate it. If I give you a simple definition of soil, it is just disintegrated rocks. Okay, let's say like this. Like I have this rock, this is a rock, just for example, and if this disintegrates into smaller pieces, so on a broad term I can call it a soil. This is just a disintegrated rock. Now what are the reasons of disintegrating it? It can be because of erosion. So because of erosion, rock disintegrates and origin of soil takes place. Now there is a very beautiful cycle in a geological cycle, which is like this. erosion will take place, that is disintegration of rocks. This soil particle will be transported and deposited and again there will be few earth movements which will again generate the rocks, and then erosion. This cycle will keep on moving. Earth movement, so we need not to bother about this earth movement. What we want to study in brief, very brief, is like erosion, how erosion take place and how this transportation take place. It is just important because we have a lot of soils which are named after this erosion and transportation agencies actually. Now first, if we talk about erosion phase, if we are talking about erosion phase, erosion can be because of two things. Erosion phase actually includes physical weathering. It actually includes physical weathering. Weathering is nothing, it's just disintegration of the rock or erosion of the rock due to the physical agents like wind, water, glacier. And actually the resultant soil particle is bulky, angular, it is rounded, it is flat. So it is just like wind striking the rock and breaking it into pieces, water coming with a lot of pressure and striking the rock, making it in a round shape or disintegrating the rock, and what we get is the soil. Second thing was the chemical weathering. Chemical weathering is sort of same, but it is like when water is containing water is acidic or basic, actually alkaline water, or there's a lot of carbon dioxide, then a chemical reaction take place which actually change the mineral content of the rock, and the rock coming out of it is a result of chemical weathering. Normally we have gravel and sand in physical weathering, like these are large soil particles, and chemical weathering results in a small soil particles like clay. We will study all this soil classification later on. We have a separate chapter for this, but we just need to understand a brief of it before starting the three-phase system. Now there is one more phenomena. This rock disintegrates. Now there are two options here, two ways. This disintegrated soil can be transported to some other place or can be at the same place. So if the soil is at the same place, we will call it a residual soil. Which doesn't get transported, it remains at the same place. And if it gets transported to some other place by some agency of nature, like maybe river, water, lake, sea water, we will call it a transported soil. What you need to know here is residual soil always has a better engineering properties compared to transported soil, if someone asks you in interview. So we should have this, like residual soils always have a better engineering properties than transported soil. Now we will name few soils which terminology you should know. We will start with, like we are clear, soil is residing there, we will call it a residual soil. What if soil is transported to some other place, we will name it according to the agency which is transporting the soil. Like suppose if we talk about water, agency is water, river water, say river water. So soil transported and deposited by river water will be called alluvial soil. If agency is wind, we call it aeolian soil. And the size of soil which they can transport actually depends on wind speed and water speed. They can even carry the boulder size, cobble size, or gravel or sand. It just depends on the speed of water, speed of wind striking the soil. Then we have even lake deposits which are termed as lacustrine soil. like a stream soil. You just need to know the terminology. At times they can ask you for 1 mark. Then we have ice deposit, soil deposited by ice, which is termed under glacier deposits. And so on. So what we just need to know here is the these few terms, and these few terms are dependent on the agency transporting them. Actually, we have various names of soil, like you can see we have black cotton soil, laterite soil, desert soil, bentone, we have bentonite, then we have bentonite, then we have calcareous, then we have humus, loam, peat. We have many actually. If we want to count it, like it's more than 20-25 on the list. But the basic concept behind these soils, very basic concept behind them is, one is the gravels, one is the soil particle size, and one is the mixture of all this thing. Like if we're going to plot the particle size on a scale, we're going to have suppose boulders. We have boulders on the top. We have boulders with like size of around 300 mm, greater than 300 mm. Then we have clay, like size of less than 0.002 mm, or say 2 micron. In between we have cobbles, then we have gravel, then we have sand, silt, clay, and so on. So all these soil names, actually they have a different mixture of all these things. Suppose if you talk about humus will be having a lot of organic soil. If you talk about desert soil, it will be having a lot of sand. So one differentiation for the naming is like particle size, and other is the mixture. Soil is having sand, clay, organic matter. According to the mixture, we are naming the soil. We will deal with all the names of the soil and size particle, and how to name them according to nomenclature in a separate chapter called soil classification. Now we'll start with the 3-phase system, which is the most basic and the most important from soil engineering point of view in a GATE and in every subject. We can't start soil engineering skipping this chapter actually. 3-phase system. Now see, before starting this point is clear. We have a rock. There are small particles after disintegrating it. Just try to understand the concept over here. If you are done with this thing, you won't have any problem in later chapters. Now this is a soil. Now what I'm doing is I'm just taking a jar with a covered cylindrical jug sort of thing, jar, and I'm putting this sand in this. So I have all the solid particles like this. Say this is 1 meter cube, or V. It's the volume of this, or take a total V total, and I'm completely filling it. Now what actually will happen is, these are all the solid particles of soil. Even if I am filling it completely, and if I try to compress this as much as I can compress it, okay fine, I can fill the voids, but still there will be few voids left. There is no way I can compress it 100%. Definitely there are going to be voids. So now what happens is, like we're going to start with the soil engineering terminology, what we will be using for the entire next soil engineering subject. Suppose this is a soil particle. This is one soil particle. We have all the soil particles like this. This is one soil particle. This is solid. Soil solid. This is soil solid. And we have few voids over here. The empty space which cannot be filled right now with the soil particles. They will definitely be there. So these are called as voids. And what we call soil, this complete phase, including solids and voids, is actually called soil. So don't confuse with the solids and soil. This is soil, this is soil. Now soil consists of solid parts which is actually the disintegrated rock, and which also has voids. Now in addition, these voids can be filled by maybe air or maybe water, maybe air, maybe water, or maybe partially air, water. Now if you want to look at this thing, now we have voids. Right now we have air in these voids. Now if I'm going to pour water from here, what I'm going to see is like few voids are covered with water. Now what I'm going to see is few voids are covered with water. So now in this my system of soil, this is entire soil, what am I having? I am having solids, I am having voids which has now air plus water. So technically what I'm naming a three-phase system. So three-phase system is solids, air and water. Combination of these three makes a soil. Now important thing to note here is we will make a three-phase diagram. We'll make a three-phase diagram on this thing, and suppose if I'm taking a jar like this and all these solid particles which I'm having it right now here, if I'm arranging in the jar, just for the representation point of view, if I'm arranging all these solid particles in the jar here and showing that okay, out of 1 meter cube, this is the entire volume of V, which is 1 meter cube. I took of the jar here 1 meter cube, this thing, and if the entire volume, out of this entire volume, I say Vs, volume occupied by the solids, is this much. And we can see we have few water in the voids also, so I can say water occupied in the jar is volume of water. Actually all the water in the jar is occupying a volume of VW, and we have a air this part, so we can say volume occupied by the air, and technically these two are the volume occupied by voids. So now right now what we have in the entire jar, this is V, the total jar volume, we have volume of solids plus volume of voids. Volume of voids can be broken down into volume of water plus volume of air. On the right hand side, how can I denote? I can denote like we have certain volume, certain solids whose volume is Vs and has a corresponding weight of Ws, weight of solids. Few solids are there in the jar whose volume is Vs and corresponding weight is Ws. Similarly, water is occupying a volume of Vw and having a weight of water. I am denoting by capital W, small w as suffix. Same thing with the air, weight of air, which is approximately equal to 0 only. So this is a basically three-phase diagram, 1, 2, 3, we can call it like this. Now this three-phase diagram can be reduced to two-phase diagram, but not to the one-phase diagram. Like suppose I am having this figure, what I can do is I have okay, same volume of solids, weight of solid will be same only. Now I am filling the entire voids with water. So what is going to happen is the water is going to occupy the space of air too. So this entire space will now belong to volume of water, and it will be volume of weight of water. So now this is two-phase. Or I can have a two-phase like this also. I can have the same jar. I can have the same jar where I have volume of solids, and this entire space can be filled by volume of air, and weight of air again 0, and I have weight of solids. So this again is a two-phase system. But now if you ask me, sir, can we have one-phase system? So actually one-phase system is not possible. We're going to have solids definitely, and we will have voids definitely. The voids will either be occupied by water or air. We can't escape both of them together. So one phase is not possible. We have two phase and three phase. So we're going to study three phase. These denominations will be used for the entire subject: volume of solids, volume of water, volume of air, weight of air, weight of water, weight of solids. And very easy, if you find total weight, what will be total weight? Very easy concept. Total weight will be equal to weight of solids plus weight of water. Total volume, volume of solids plus volume of water plus volume of air. Now if you are done with this concept thoroughly, so there is nothing much left in soil engineering. It will be very easy to go with the important definitions now. But if you understand this concept and these denominations, you will find those definitions very easy. Now one thing to be noted here is, in the entire soil engineering, now what the game is just play with the content of water, play with the content of air, and play with the content of solids. We will keep on modifying these three things, and we will find that soil strength is changing. Actually, if you're going to increase the WS, weight of solids, more, then we will find that soil is becoming more and more dense. So we'll look after each and everything in next chapter, but I will start with right now water content. Like there are few definitions. These definitions actually tell the characteristics of the soil. Like you will understand once we begin with this important definitions. First one is the water content. Also I can call it as moisture content. Moisture, water, same thing. Moisture content. Definition itself says it shows the amount of water content in the soil or moisture content in the soil. It is simply a ratio. Now ratio of weight of water in the soil by weight of solids in the soil. Solids, water. We made this diagram. Like we have weight of solids, volume of solids, we have volume of water, weight of water, we have volume of air, weight of air. Now I'm talking about the ratio of weight of water by weight of solids. Now if we look on to the limit, like we want to represent this water content by W, a simple W. Okay, this is a small w, and total weight was capital W, which was equal to WW, weight of water plus weight of solids. Now we talk about the water content. So water content can be equal to 0, obviously, if I reduce the weight of water to 0. If I neglect this thing, if I just minimize this water to 0, and if I just have weight of solids and weight of air, so yes, water content can be equal to 0. So this W can be equal to 0, right? So I can write, but what about the upper limit of this W? I can have a system like this too, where weight of solids is just this much, and I have this entire filled with weight of water. So technically what I can say is that water content doesn't have a upper limit. Water content, yes, can be equal to or greater than 0. Equal to 0 when the soil is entirely dry, it is not having any water content. Entirely dry soil will be having a water content equal to 0. And when soil is having a lot of water, maybe more than WS, so we can't say that it has any upper limit. It can go be 10, 20, 30, 40, even 500. But practically it's not possible. Practically it is possible, but practically we don't consider that soil to be feasible for engineering functions. Now second, what we're going to talk about is the void ratio. Void ratio term itself defines it's something we are talking about, void, and then ratio. So it is technically represented by E, small e. Small e is equal to volume of voids, whatever volume of voids we are having, to the ratio of volume of solids. This will be greater than 0 always, because as I told you that it is not possible to reduce volume of voids to 0. In no case we can reduce volume of voids to 0. volume of voids will be there. We can just reduce the number, but we can't reduce it to 0. So volume of voids will be there, but we can't reduce the number to 0. But if we talk about the upper limit, again we don't have any upper limit for this, because we can have this much volume of solids, we can have this much volume of voids. There is no upper limit of this. If we divide VV by VS, we don't know what this ratio will be. We don't have any upper limit for void ratio. But actually water content and void ratio defines the soil, defines the denseness, defines the water content, defines the void ratio in a soil. So these two becomes very engineering terms for defining a soil. Then we're going to start with porosity. Third term, porosity. It is represented by N. It is the ratio of volume of voids by total volume. I can write capital V or suffix T. Volume of voids by capital T. Earlier, if I talk about void ratio was volume of voids by volume of solids. Porosity is actually volume of voids by total volume of soil. This is the total volume of soil, and out of which I am having volume of voids. Suppose like this. This is volume of voids, this term, and this entire is volume of solids. So this actually has the upper limit. This volume of voids can be maximum to the volume of soil. It can't go beyond this thing, and it has a what is the least value? It can't be 0 again. Volume of voids can't be 0. So what I can say is porosity can be somewhere greater than 0, but not greater than 100% basically. It's a ratio